afternoon, children. Now yesterday we had talked about Coulomb's law and Coulomb's law in vector form. I think you might have understood and might have done the numericals which I had given. Now we'll talk about Coulomb's law in position vector form. Coulomb's law in position vector form. Now you have done position vector in class 11. That is, if I want to define the position of a given object, then I use position vector. For determining the position, we have to take a reference. So, of reference is always taken as 0, 0. Like suppose if you are sitting at a particular place in the room, say next to some other student. So, if I ask you where are you sitting, what you will tell me? I am sitting next to him. And if I ask the other student, the same one, he will say I am sitting next to him. So that means you are giving your position with respect to each other. But I will not be able to know the exact position of yours where you are sitting. For me, the exact position will be defined only when you will tell me your position in reference to someone. Like if I ask you, where do you live? So you will tell me, I live next to, say, SRS Cinema Hall, or you will tell me I'm there in the vicinity of exhibition ground, or the colony's name, or the road's name. So that is the reference, and reference can be taken anyone which everybody knows. So most of the time what reference is taken as 0, 0. Now we have again going back to Coulomb's law. Suppose there are two charges, say Q1 and say Q2 at a distance, say R apart. Now I do not know this distance R. I know what? I know only the position of Q1 and I know only the position of Q2. I don't know what the R is. So how to calculate this R? Now position of this vector, this charge is known to me from a reference point. So what I'll take? Say this is the reference point. So this will be, say, my vector R1. So R1 is the position vector of charge Q1. Similarly, R2 will be the position vector of charge Q2. Now, if I know the position of these two by position vectors, say R1 and R2, now I can easily find out what is the value of R. How? I use now here, say, vector addition. Triangular law of vector addition. And by that law, depending upon the direction of force from Q2 to Q1 or Q1 to Q2, I have different values of R. Suppose I take the value R1, 2. Force on 1 because of 2. So this will be, as we did earlier, 1 by 4 pi epsilon naught Q1 Q2 upon R square. This R is to be replaced by position vector now. Multiplied by a unit vector in the direction of force. Now what is the direction of force? Force on Q1 because of Q2 will be in this direction if both the charges are same. That is positive charges or negative charges. So this is the case for similar charges. That means this is the direction. So R12 is having direction from 2 towards 1. So this will be replaced by now force on 1 because of 2 is along R2 1. As far as the magnitude is concerned, magnitude of R21 will always be equal to R12, and that will also be equal to, say, R. Only the direction is different. Now from vector addition, what is the value of R21? It will be R2 plus R21 must be equal to R. Law of vector addition. Tail to head, and tail of the first vector to the head of the second vector will give me the result. So what will be R21? R1 minus R. So I have to only substitute here now the value of R21. So what I'll do? R21 vector divided by magnitude of R21, and this also can now be replaced by R21 vector and square of its magnitude. And this can be now further written as 1 by 4 pi epsilon naught Q1 Q2 upon R21 can be written as R1 minus R2. R1 minus R2 divided by R1 minus R2 whole cube. Now this is square. This is 1 power only. So R1 minus R2 cube. In this way we can find out force on 1 because of 2 in terms of position vector. That is, position vector means, again I am repeating, if we do not know the distance between the two charges between which force is to be calculated, we have to take the position of Q1 separately, Q2 separately, and then find out the value of R or R21 or R12. Similarly, we will now find out F21. The only change will be now F21 here, and now the direction of force will be towards this side, that is R12. So 21 here and 12 here, that will be changed. Suppose if the two charges are not similar, one is positive and the other is negative. So like we did yesterday, it is in the same manner. The only difference is now the directions will again change. Suppose this is a positive charge and this is negative. Then the force on 1 because of 2 will have this direction. And now F12 will be 1 by 4 pi epsilon naught Q1, Q2, R12, R12 and R12. These will be interchanged. See, as far as Coulomb's law in vector and position vector is concerned, these are not to be learnt as such. These are mainly to understand so that numericals can be done correctly. Because these are concerned with not the magnitude, only the direction. So when we calculate force on a particular chart, we have to keep in mind direction first, and accordingly they will be added or subtracted. Now suppose if there are more than 2 charges, then what will happen? Then we will go with the superposition principle, which we state for multiple charges. Suppose there is a charge Q and around it say there are many charges due to which it can feel a force, say up to Qn. Now, according to superposition principle, if I want to calculate the force on charge Q, then force on charge Q will be separately a sum of charge on Q, force on Q because of Q1. Considering only charge Q1 first. Force on charge Q due to Q1 plus force on charge Q due to Q2 plus force on charge Q because of Q3 and so on. So what will the force? Net force? It will be force on charge Q because of charge 1 plus force on charge Q because of 2. You can write on Q1 also like this. Q1, Q2 plus force on charge Q because of Q3 and so on up to force on charge Q due to charge Qn. And this forces now you already know how to calculate. Clear? So in this way, superposition principle can be used. Using the superposition principle, try to do first the solved examples. In your NCERT book, that is example 1.6 and example 1.7 on page 16 and page 70. By doing those two exercises, it will be more clear to you how this superposition principle is being used for calculating the force on a particular charge due to many other charges. Thank you. In the next video, we'll talk about if the charge is not a point charge, then how to use Coulomb's law to calculate force. Now we'll talk about how the Coulomb's law can be used when the charge is not a point charge, but it is distributed over, say, a given line or a surface or a volume. Suppose the charge is distributed over a given line, that is known as linear charge distribution. Suppose the charge is distributed over a line, say of given length, on a given length, say 0 to n, like this. And the charge is continuously distributed and the charge is Q. Here we define one new term which is known as linear charge density. Linear charge density. That is charge upon the length over which the charge is distributed. And see how you can now use the Coulomb's law. Suppose I want to find out a force between this linear charge distribution and say a charge Q naught. Now the distance from different points of linear charge distribution will be different for this Q naught. So what I'll do is, I will take and also the Coulomb's force is applicable only for point charges. So I take a very small length, say dl, of this linear distribution, considering that charge in this much length is say dq, and this charge dq can be considered as a point charge. And once this charge is considered as a point charge, I can use Coulomb's law. So the force on charge Q naught because of this distribution will be equal to 1 by 4 pi epsilon naught q naught dq upon, say if the distance of this from this q naught is say r, then r square. Now I use this concept of linear charge density. Linear charge density is denoted by lambda. So lambda, as it is q by l, this will also be equal to dq by dl, because distribution is, we are considering as uniform. So what is now dq? dq is now equal to lambda into dl. Now substitute in this place, f is equals to 1 by 4 pi epsilon naught q, and now in place of dq I can substitute lambda dl upon r square. Now this is clear now. See, when I have talked about the force on q naught because of this charge dq, now that is not the total force exerted by the total length. It is only because of dl. So that means this is not the total force but df. So this will be also equal to df. For finding out f, I'll integrate this expression. An integration you are already familiar with the limits 0 to f. And in this way, Coulomb's law can be used to find out the force between two charges in which, say, one of the charge is not a point charge, but it is distributed over a given length. This concept will also be used in Gauss's law when we'll be finding out electric field using Gauss's law. Now, if you have understood this linear charge distribution, then you'll be able to understand the surface as well as the volume. Now, as I said earlier, the charge can be distributed over a given length. The charge can also be distributed over a given surface. Then in that case, we define in exactly the same manner surface charge distribution, and will now define another physical quantity, that is surface charge density, and now it will be Q upon the area of the surface. And what you do exactly in the same manner, we'll be doing it again. Let there be a surface with charge, say, Q over a given surface, and say area as A. And I want to find out the force on charge, say Q naught, because of this surface charge, which is Q over a given area A. Again, what we are going to do is consider a small surface area, say dA, and which can be considered as a point charge, and the charge contained in this small area will be now dq, which will be considered as a point charge. The distance between them, say r. What is the change? It will be the same. df will be equal to 1 by 4 pi epsilon naught q naught dq upon r square. Now here I'll change it with sigma. Surface charge density will be denoted by sigma. So sigma is dq upon dA here, and accordingly dq will be replaced by sigma into dA. So in place of q, I'll write down sigma into dA. Sigma into dA. If this is q naught, I'll take it as q naught. Alright? And And in this way, again, you'll get an expression. Exactly in the same manner, I think now you'll be able to do the next one. You might have understood how it is to be done. So now, the third one, volume charge distribution, which will denote by rho. Here I'll take volume. Here we'll consider a small volume. So the charges, say again Q over a given volume, say V. I'll take a small volume. Charge, say dq volume dV, and accordingly change the expression. In this way, we can use Coulomb's law to find out force due to continuous distribution of charge. So I think you'll be able to do this, go through all these things, do the solved examples which I have given to you, and tomorrow we'll talk about electric field. What we have talked so far is electric force. So one phenomenon, electric force, is being told to you, which is due to a point static